In this video, we are going to talk about one of the applications of derivatives that is fairly useful to be aware of. And so this is the idea of related rates. So related rates is a way of feeling out how one thing is changing with respect to time when you know how another thing is. So to kind of motivate this, consider the following. So suppose we pump air into a spherical balloon so that the volume increases at a rate of 100 centimeters cubed per second. We want to know how fast the radius of the balloon increases when the diameter is 50 centimeters. Now, this is a pretty realistic situation to be in. So we've got this balloon that's spherical in shape. Balloons usually aren't spherical, but we're going to assume spherical just to make the formula easier. You can do it with non-spherical balloons. It just adds more geometric issues, but they aren't really calculus issues. So we've got this balloon that we're pumping air into. Now, it's pretty standard to have an air pump to actually pump air in, so you know the rate that the air is going in, which is just telling us how the volume is increasing. So the volume is increasing at a rate of 100 centimeters cubed per second. And we want to figure out how fast the radius of the balloon is increasing, specifically when the diameter of the balloon is 50 centimeters. Now, you might want to know this because you might want to make sure you're not pumping air in too quickly to pop the balloon or something like that. And so there are a number of reasons why you might actually care about the rate that the radius is increasing at. And what we're going to do is we're going to use the fact we know the rate of the volume change to figure out how the radius is changing. And so let's make some notation. So we're going to let V be the volume. T is going to be time. And R is going to be the radius. Now, in related rates questions, time is always going to be our variable. So all of the derivatives and everything in related rates questions are going to be with respect to time. And we're given that the rate that the volume is changing is 100 centimeters cubed per second. So dV over dt is 100 centimeters cubed per second. And we want to know the rate the radius is changing. So we want dr dt when r equals, well, the diameter is 50, then the radius is going to be 25. So remember, the radius of a circle is just half the diameter. So the radius is going to be 25 if the diameter is 50. And so this is the information that we have and what we want. So now what we're going to do is we're going to use the fact that we know how the radius and the volume of a balloon are related to figure out how the rates are related. And so as a reminder, the volume of a sphere is equal to 4/3 pi r cubed. And so this is just a formula, but that tells us how the volume and the radius are related. And now to figure out how the rates are related, all we're going to do is we're going to take the derivative implicitly with respect to time of each side. And so we're just going to take the derivative with respect to time of v, and the derivative with respect to time of 4/3 pi r cubed. Now, the derivative of v with respect to time is just dv over dt. And then to take the derivative of 4/3 pi r cubed, we have to use the chain rule because we're taking the derivative with respect to t. So we're going to have 4/3 pi, because those are all constants. Then the derivative of r cubed with respect to t. So it's 4/3 pi. The derivative of r cubed will be 3r squared dr over dt. Because we have to use the chain rule, And so the derivative of r cubed gives us 3r squared, but then we have to multiply by the derivative of r, which is dr over dt. And so this then becomes 4 pi r squared dr over dt. And so we've got our relationship now between dv over dt and dr over dt. And so now we wanted to know dr over dt when the radius is 25. And so we're going to plug in our information that we know. So we're going to plug in known information. Okay. And so we know the radius is changing at a rate of 100. So dv over dt is 100 centimeters cubed per second. Then we have 4 pi, r is 25 centimeters, so we'll have 25 centimeters squared, then dr over dt. Now we want to solve for dr over dt, so we're just going to divide 100 centimeters cubed per second by, if you actually multiply this out, you would get 4 pi times 625 centimeters squared. And so simplifying this then becomes 1 over 25 pi. And then if you actually keep track of the units, we have centimeters cubed by second over seconds divided by centimeters squared, so we'll just get centimeters per second. And those are actually the units that the radius would be changing with respect to. And so the rate of change of the radius when it is 25 centimeters is going to be 1 over 25 pi centimeters per second. And now it does depend on what the radius is, because if you think of the sphere as you make the sphere bigger and bigger, the radius is going to grow at a slower and slower rate because there's more and more air to fill up to make the radius get bigger as you expand it. And so this is the idea of a related rates question. And so we're going to do another example of this. That's most of what this video will be, is just different ways of doing these problems. But the feel of them follows the same pattern that we just used. So our next example is we're going to have a ladder that is 10 feet long, resting against a vertical wall, has the bottom sliding away from the wall at a rate of 4 feet per second. We want to find how fast the top of the ladder is sliding down the wall when the bottom of the ladder is 6 feet from the wall. Okay, and so in related rates questions, it is helpful to actually draw a picture of the situation. So let's draw a picture of what is actually going on. And so what we have here is we have this ladder, and we know the ladder is 10 feet long, so the length of the ladder is going to be 10 feet. And we've got this wall here that it's resting against. This is going to be the ground. And we know it's sliding away from the wall at a rate of 4 feet per second. And we want to figure out how fast it's going down. So this is what we want. We want to know the speed that we are sliding down the wall. So to do this, we're going to assign notation, kind of like we did before. And so we're going to let x be the distance that we are away from the wall, and y is going to be the distance that the top of the ladder is from the ground. So y is just literally this distance here, and x is this distance here. So now using these variables, we can write down the rates that we have in terms of x and y. And so we're told that we're sliding away from the wall at a rate of 4 feet per second. So dx over dt must be 4 feet per second. And we want to know how fast we're sliding down the wall, so we want dy over dt. And we care about that when x is 6 feet. So we care about it when we're 6 feet away from the wall. And so what we need to do is we need to find some relationship between x and y. Well, notice that this is a right triangle that we have here. And so the Pythagorean theorem relates all three sides of the triangle together, and x and y make up two of the sides, so that gives us a relationship. We have x squared plus y squared must equal the hypotenuse, which is 10 squared. So in other words, x squared plus y squared equals 100. So this is a relationship between x and y. Now that we have a relationship between x and y, we're going to take the implicit derivative to get a relationship between the rate of x and the rate of y. And so we're going to take the derivative with respect to t of both sides. And so taking the derivative of x squared plus y squared implicitly, this is going to be 2x dx over dt plus 2y dy over dt. And then the derivative of 100 is just 0, because 100 is a constant. Okay, and so we're just doing the chain rule here, implicit derivatives that we've talked about before. Now we care about dy over dt, so let's actually solve for dy over dt. So we have 2y dy over dt equals negative 2x dx over dt. Dividing both sides by 2y. We then get that dy over dt is equal to negative x over y dx over dt. And so this then is a relationship between dy over dt and dx over dt. Now we have information that we want to plug in to figure out this rate. So remember, we know dx over dt is 4, and we care about this when x is 6. And so x is 6, and dx over dt is 4. But notice we have a y showing up on the right-hand side as well. So we need to figure out the value of y. Well, the value of y that we care about is the same as when x is 6. And so rather than having y just be some arbitrary value, we only really care about what it is when x is 6. And so from our triangle, when x is 6, we have the following setup. And the value of y we care about is just this side of the triangle. So we're going to use the Pythagorean theorem again. So we have 6 squared plus y squared should be equal to 10 squared. So 36 plus y squared equals 100. Then y squared equals 64. So y equals 8, which is the square root of 64. Now we take the positive square root here because y is obviously a positive number. The ladder is not below ground, so we know y is positive. So the value of y we care about is when it's 8. And so in that specific point in time we care about, x is 6 and y is 8. So now we can plug in our known information to get dy over dt. Now x is going to be negative 6. We're going to have negative x, so negative 6, and that's in feet, divided by y, which is 8 feet, times dx over dt, which is 4 feet per second. And so multiplying this out, we're going to get negative 3/4 times 4, and then just in feet per second, the units of feet cancel on x divided by y. Now, multiplying this out, we get negative 3 feet per second. And so that then tells us that the rate at which we are sliding down the wall is 3 feet per second. So we were able to figure out how the y value is changing, knowing how the x value is changing. So now that we've done 2 examples of this, you may have noticed a pattern that we're kind of following in doing these problems. So I'm going to write down the steps to a related rates question. I didn't do this to start with, as I think actually seeing the process and kind of logicking through it can be helpful. But there are steps to follow. So these are the steps to a related rates question. So step 1, these come from a textbook, so just be aware the first step is kind of dumb, but it says read the problem carefully. Make sure you actually are reading the question. That's really all I have to say there. Step 2 is draw a diagram, if possible. So sometimes a picture is not easy to draw, but if you can draw a picture of the situation, it'll help you logic through what's going on a lot easier. Step 3 is introduce notation. So this is just assigning symbols to all the variables. So assigning symbols to all variables present. Step 4 is express the given information and the required rate in terms of the notation. So this is basically just actually writing down, like, we know dx over dt is this, dy over dt is what we care about, things like that. And so it's just basically using the notation that we have to actually express the stuff in the problem. Step 5 is write an equation that relates the various quantities of the problem. Now there is an important caveat here. And so if necessary, use geometry to eliminate the variables you don't know the rates of. Now this problem doesn't come up often, but sometimes you will have some value in your equation that you just don't know the rate of. We're going to do an example of that in a second, but when that is the case, you want to eliminate that variable before taking the derivative or anything because you don't know its rate. And we use geometry to do that. And like I said, there will be an example of that in a second. Then step 6, use implicit differentiation to find a relationship between the rates. And just to be clear here, we always differentiate with respect to t. So in related rates, we're always assuming that time is our variable of things changing. In reality, you could do this same process if you had some other variable affecting multiple things, but we're only going to really worry about time in this lecture. as that's the one that's most common. The other situations are kind of contrived. But you could use something similar if you had one variable affecting multiple things. And then step 7 is substitute the known information into the resulting equation and solve for the unknown rate. So this is basically plug all of your numbers in. So plug all the stuff you have in, solve for the value you care about. Now, one important thing to be aware of, and this is where related rates questions can be messed up, is you should not plug things in too early. So a warning, do not plug in values until after you differentiate. And so to kind of point out what I mean here, I'm going to scroll up to that problem we did before. And so in this problem here, before I plugged in the fact that x was 6, I took the derivative. The reason for that is because I only care about the rate when x is 6. But x isn't always 6. X is changing, right? X is changing at a rate of 4 feet per second. And so it is not a fixed number. And so I can't just always assume it's 6. I only care about what's happening when it's 6. But that's different than saying that it actually is 6. So you need to make sure you take the derivative before you plug stuff in. Otherwise, you might have some variable that's actually changing where you only cared about it at a fixed point in time. The fact it was changing was very relevant still. Okay, so we're now going to look at another problem. And as I mentioned before, in this problem, we're going to have the situation where we're going to have to use geometry to eliminate some stuff. And so we have a water tank in the shape of an inverted cone with base, radius 2 meters, and height 4 meters. Okay, so we've got this cone of tank, and we want to know if water is being pumped into the tank at a rate of 2 meters cubed per minute. We want to find the rate at which the water level is rising. When the water is 3 meters deep. Okay, so let's draw a picture of our situation. So we have this cone here. We know that the top radius is going to be 2. The full height of this cone is 4 meters. These are both in meters. And then water is being added to the tank. So at some point we have our water level. We have our radius here, r, and we have some height of the water, which we're going to call h. And so we're just saying that this is the picture when we have rose the water level up to h. And we're adding water in. So we're adding water to the tank at a rate of 2 meters per minute, meters cubed per minute. Okay, and so we're going to use kind of the standard notation of r for the radius, h for the height, and v for volume. So that's just kind of the standard notation when you're dealing with volumes. And so steps that was step 2, so we're going to do step 3 and 4 now. So we care about dv over dt being 2 meters cubed per minute. That's what we know. And we want to know dh over dt, the rate that h is changing, going up, when h equals 3 meters. So we've assigned notation and written down what we know in terms of that notation. Okay, and so now step 5 is where the kind of the hard part of this problem comes in. So we want a relationship between the volume and the height. Well, one relationship we know is the volume of a cone is 1/3 pi r squared times h. Now notice in this problem that the radius is going to change. So as I add water, the radius is going to change and the height is going to change. But I don't know how the radius is changing. Okay, that's not something we were given. We don't know what dr over dt is. And so we want to replace r in this equation before we take the derivative. That way we don't have this variable that we don't know about showing up. And so that's kind of why you have to do the following step of getting rid of r, because we just don't know how r is changing. And we don't actually care about how r is changing either, other than if it shows up. So now the way we're going to do this is we're going to think about taking a cross-section of the cone. So I can't draw this very well graphically, but what you can think about is as if we're going to cut the cone like directly in half, and we're just going to take a cross-section of it. So think of the cone kind of being made flat. And so the cone, if we made it flat, would look something like this, where I will try to draw things still how they were before. And so cutting it in half, I realize I didn't make that symmetric, but cutting in half, this is going to be the distance r. This was still our water level, so that's the water level we had before. So h is then how tall that is, and then we were told this is 2 meters, and this is 4 meters. And so we've got this situation here, and we want to figure out how r and h are related. And so what we're going to do is we're going to use similar triangles. And so similar triangles says that corresponding sides are related in a ratio. And so if I look at r divided by 2, that's the same as h divided by 4. And so r divided by 2 equals h divided by 4. So that's just how similar triangles work. So we have two triangles that are similar in size. We have the big triangle, which I'm drawing in red, and then we have the blue triangle, that's the water level. And so the corresponding sides, which are r and h, are going to relate with r over 2 being related to 4 over h, because 4 and h are the lengths of this vertical side. Okay, so we have those similar triangles that give us that relationship. But now we want to know how r is related to h, so I'm just going to multiply by 2. So that tells us r equals h over 2. So this gives us a relationship between r and h. And this relationship will always be true because as I fill up the water tank, we still have similar triangles. I didn't make any assumptions of how much water there was in the tank, so we always have that r equals h over 2. So we're going to plug that in to v. So v equals 1/3 pi r squared h, but we know that r is h over 2. So I'm going to just replace r with h over 2 to get 1/3 pi times h over 2 squared times h. And if you multiply this out, we get pi over 12 h cubed. So now this is a relationship between v and h that only involves v and h. So it only involves the things we either know the rate of or care about the rate of. And that's what we mean in step 5 when we say use geometry to get a formula that only involves things we care about. And so that is step 5. So now we're on to step 6. In step 6, we take the implicit derivative, and so we're going to have that dv over dt equals the derivative with respect to time of pi over 12h cubed. And so this will be pi over 12 times 3h squared dh over dt. And so simplifying this, we get pi h squared over 4 dh over dt. And so now I want to solve for dh over dt. So I'm going to multiply both sides. Well, actually, write it down again. So we have dv over dt equals pi h squared over 4 dh over dt. Now, dh over dt is the thing I care about. So I'm going to multiply both sides by 4 divided by pi h squared to get dh over dt by itself. And so this gives us our relationship of dh over dt equals 4 over pi h squared. And so that's a relationship of dv over dt. So this is a relationship between the rate of h is changing and the rate v is changing at. So now what we're going to do is we're going to plug in the information that we have. So that is step 7. So we're just going to plug in the information that we know. So dh over dt equals 4 over pi. And now h, we remember, if you scroll up, that we care about this when we are 3 meters deep. So we care about this when h is 3. So we're going to have 3 meters squared times the rate that the volume is changing at. And the volume was changing at a rate of 2 meters squared per minute. Okay, and so we then have this, and so multiplying things out, we're going to get 8 over 9 pi. This should be, I said meters squared, this is meters cubed. Volume is cubed, not squared. And so this is going to be 8 over 9 pi, and then we're going to have meters per minute. And so the rate that the height is changing at is 8 over 9 pi meters per minute. And so we were able to compute this by using similar triangles to eliminate r in our equation. So let's look at another example now. So we have car A is traveling west at 50 miles per hour, and car B is traveling north at 60 miles per hour. Both are headed for the intersection of the two roads. At what rate are the cars approaching each other when A is 0.3 miles and B is 0.4 miles from the intersection? Okay, so as before, what we're going to do is we're going to start by drawing a picture. And so we have these two roads, and we have car A is on this road, and it's traveling to the west, so to the left, at a rate of 50 miles per hour. Car B is down here, and it's traveling north at a rate of 60 miles per hour. And we want to figure out the rate that the distance between them is changing. So the distance between them is going to be this value, which I will call z. Now, as we typically use x for horizontal distances, I'll call this x and this y. And so x is going to be the distance here. It's the distance from the intersection to A, and y is the distance from the intersection to B. Now, the reason why this is relevant is x and y are actually going to be getting smaller. And so we are shrinking the value of x and shrinking the value of y with how we've written things. And so that means that dx over dt is going to be negative 50 miles per hour, and dy over dt is going to be negative 60 miles per hour. And this makes sense because, like I said, x and y are getting smaller. So even though the speed of the cars is positive, the direction is giving us the negative sign. And we care about this when x is 0.3 miles and y is 0.4 miles. Okay, so now we need a relationship that's going to relate x and y to z's rate. We didn't write that down. What we care about is z's rate. So we care about dz over dt. Okay, we want to know how fast the distance between them is changing. So we want some relationship between these variables. Now, we have a right triangle, so kind of the most obvious one to use is the Pythagorean theorem. So we have z squared is equal to x squared plus y squared. Now, unlike in the previous example, we know the rate of both x and y. And so we don't need to replace them because we know how fast they're changing. And we care how fast z is changing. So we don't need to do anything with this equation to eliminate things, because everything that we have, we either know the rate of or care about the rate of. And so we're just going to take the implicit derivative from here. So we're going to take the implicit derivative with respect to t of both sides. That squared should be in the parentheses. So the derivative of z squared is going to be 2z dz over dt is equal to 2x dx over dt plus 2y dy over dt. Now we want to figure out dz over dt, so I'm going to divide by 2z. So that gives us that dz over dt is equal to x over z dx over dt plus y over z dy over dt. Okay, so this gives us a relationship between the rate that z is changing at and the rate x and y is changing at. And so now we know most of these variables. So we know x is 0.3, we know y is 0.4, we know dx over dt is negative 50 miles per hour. These are miles. And then we know dy over dt is negative 60 miles per hour. But we do not know the value of z at the moment. We've done this type of thing before, though, so we just need to figure out what z is at that specific point in time we care about. So if we draw our situation that we actually care about, we care about the situation when x is 0.3, y is 0.4, and we just need to figure out what z is at that point in time. And so using the Pythagorean theorem, z squared equals 0.3 squared plus 0.4 squared. So z is going to be the square root of 0.3 squared plus 0.4 squared, which is equal to the square root of 0.09 plus 0.16. So the square root of 0.25, which is 0.5. And so the value of z is 0.5. So now we know the value of z at that point in time we care about. So we're just going to plug everything in. So dz over dt is equal to x, which is 0.3, miles, divided by z, which is 0.5 miles, times dx over dt. dx over dt is negative 50 miles per hour. And then we're going to add to that 0.4 miles, that's y, divided by z, which is 0.5 miles, times dy over dt, which is negative 60 miles per hour. And so note, in terms of units, the miles are just going to cancel from x divided by z and y divided by z. And so we then have, if you just simplify this, this is going to end up being negative 78 miles per hour. And so that tells us then that the cars are approaching each other at a rate of 78 miles per hour. And it's negative again because the distance between them is getting smaller as the cars get closer to each other. So now we're going to do one more example. And so we have a man walks along a straight line at a speed of 4 feet per second. A light is located on the ground 20 feet from the path and is kept on the man. So you can think of this as like you have an actor on stage and you have a spotlight that you're trying to keep on the person. So the spotlight is 20 feet away from the man, and the man's walking along the stage at a rate of 4 feet per second, and you're just trying to keep the light on the man. And so we want to know at what rate the light is rotating when the man is 15 feet from the point on the path closest to the light. Okay, so let's actually draw this situation. So we've got this path here, and we've got this light down here. The light is 20 feet away from the path at the closest point, which the closest point is going to be perpendicular. Hopefully that's easy enough to see. And we've got some man over here. And the man is moving at a rate of 4 feet per second. And so we've got this light is shining on the man, so the light has to be shining there. This angle is the angle of the light. And the man we care about when he's 15 feet away from that point. So we care about it when this distance is 15 feet. Okay, so this is the situation, and the man is moving to the right in my picture at a rate of 4 feet per second. Okay, so as usual, I'm going to let x be our horizontal distance. So x is going to be a horizontal distance. So we know x is 15 feet when we care about it. Dx over dt is going to be 4 feet per second. And it is going to be positive this time because the man is moving to the right, so the distance is getting further. And what we care about is the rate that we're rotating at. So we care about d theta over dt. Okay, so we need a relationship between x and theta. And so this one is a bit trickier, as you might not immediately see a relationship, but we care about theta here. Theta is an angle, and we have a right triangle here. And so we're going to just relate the sides that we know about and care about. Well, we know the length 20 is fixed, and we care about x. So we have that x over 20, this is the opposite over adjacent sides of this triangle, and that's tangent. So we have tangent of theta equals x over 20, or if you prefer, x equals 20 tangent of theta. So this gives us a relationship between x and theta now. And notice that we know the rate of x, we care about the rate of theta. There aren't any other variables here, so we don't need to do anything special at this point. So now we're going to take the derivative with respect to t. So we get dx over dt equals the derivative with respect to time of 20 tangent of theta, which is going to be 20 secant squared of theta d theta over dt, because the derivative of tangent is secant squared. Now remember, this equals 20 divided by cosine squared of theta, d theta over dt. The reason why that is relevant is we want to solve for d theta over dt, and it's a little bit easier to think about it when you write it at secant as 1 over cosine. So I want to solve for d theta over dt, so I'm going to multiply both sides by cosine squared of theta over 20. So then what we've got here is d theta over dt is equal to cosine squared of theta over 20 dx over dt. And now we care about this when x is 15 feet, and dx over dt, we are told, is 4 feet per second. But notice that x doesn't actually show up on the right-hand side. Rather, cosine of theta does. So what we want to do is we want to figure out what is cosine of theta when x is 15. So drawing our triangle. When x is 15, this side is always 20, and we've got this side over here, which I'll call z, and theta is this angle right here, and so we want to figure out what theta is, what cosine of theta is. Well, cosine of theta is the adjacent side, which is 20, divided by the hypotenuse, which is z. So we need to figure out what z is in this formula. Well, using the Pythagorean theorem, we can figure that out. And so the Pythagorean theorem tells us that z squared equals 15 squared plus 20 squared, which is 225 plus 400. So z squared equals 625. Taking the square root, you get z is 25. So z is then 25, so cosine of theta is 20 divided by 25, which is 4/5. So that is then what cosine of theta is. So let's plug that into our formula. So we have d theta over dt equals cosine squared of theta. Cosine squared, though, is 4 over 5. So we have 4 over 5 squared divided by 20 times dx over dt. Well, dx is 4 feet per second. And so we're going to have 4 feet per second here. And then this is 20 feet, just as a reminder, because that was the length that we were getting from before. And so this then gives us a value of 16 over 25 times 1 over 5. And then the feet cancel, so this is just per second. Now, radians don't have a unit. That's kind of an interesting fact about radians. So while we're just going to have like nothing per second for our units, it's actually radians per second. Radians are just a unitless thing. But because it looks weird to just write per second, I'm going to write radians per second. And so that gives us that d theta divided by dt is equal to 16 over 125 radians per second. And so that is then the rate that the stoplight needs to be rotating at to stay on the man.